In this video, we're going to look at applying the inverse trigonometric functions that we've been learning to solve an application or story problem. So here's the story problem. It says viewing angles at an art show. So not a problem that I wrote. I can't remember who I stole this from. I should attribute it, but I can't remember where I got it. At an art show, a painting 2.5 feet in height, so 2.5 feet here, is hung on a wall so that its base is 1.5 feet above eye level of an average viewer. So here's the line that represents eye level of an average viewer. And the question they want to ask, they want to go straight to, is determine the distance x to tenths of a foot that maximizes the viewing angle. This is the viewing angle right here, the angle at which you're seeing the image. That's what they want to ask. Now what they're thinking is that this problem's a little bit difficult for beginners. So we're going to scaffold you. We're going to have you get the pieces that you need to answer the actual question in part C by having you come up with them one step at a time. So when you get a problem like this where it's a multi-part problem, sometimes it's actually better to read the last question first, because usually that's going to be what you're really trying to find. Determine x that maximizes theta. What is the x that maximizes theta? So we'll step through the scaffolded problem now. It says use inverse functions to find expressions for angles alpha and beta. So here's alpha. Alpha is this big angle here, and here's beta. Beta is this baby angle right here. And what I want to recognize is that both alpha and beta are associated with right triangles. So I can use right triangle trigonometry to describe beta. And I want to identify that I know the side opposite beta is 1.5 feet and the side adjacent beta is x, which means I can describe the situation using the tangent function. The tangent of beta is the side ratio given by the side opposite beta and the side adjacent beta. And then it says find expressions for beta, which means I need to solve for beta. So I'm going to take the tangent inverse of both sides. Tangent inverse of tangent of beta equals tangent inverse of the side ratio 1.5 over x. And clearly beta is an angle between 0 and 90 degrees, so it's going to be in the range of the tangent inverse function. So when I apply the tangent inverse, I'm going to get the angle beta that's between 0 and 90, and it's going to equal the tangent inverse of 1.5 over x. And the thing to note here is you usually could skip from here straight to here, but I wanted to emphasize that the tangent inverse is what's digging beta out of the tangent function. So I'm going to put a star by this because we'll need this. And then it says find an expression for alpha. So alpha is this larger angle here. And the side opposite alpha on this right triangle is 2.5 feet plus 1.5 feet is 4 feet. And x is the side adjacent alpha. So I can describe alpha as using the tangent function as tangent of alpha is the side ratio 4 over x. And then I take the tangent inverse of both sides, which digs theta out and leaves me with the tangent inverse of 4 over x. And I'm going to hang on to this because for part B, it says use the result of part A to find an expression for the viewing angle theta. And what I want to notice is that theta, the viewing angle, is the difference between alpha and beta. In other words, theta is just equal to the large angle alpha minus the smaller angle beta. And theta isn't on a right triangle. This isn't a right angle. This is an obtuse angle. This is an acute angle. I can't use right triangle trigonometry to get at theta directly, but because I can describe it in terms of alpha and beta, which were involved with right triangles, I now have a way to express it. I can replace alpha with the tangent inverse function. So tangent alpha is the tangent inverse of 4 over x. minus beta, and beta is the tangent inverse of 1.5 over x. So tangent inverse of 1.5 over x, and that's what theta equals. So part C says use a calculator to help determine the distance x to tenths of a foot that maximizes this viewing angle. So before I jump into just going into the calculator and graphing, I want to think about what's a reasonable range of values for x to be. Like, what interval should x live on? X can't be negative, then I would be through the wall. If x is 0, I have my nose right up against the wall. And am I going to stand 100 feet from the painting? Probably not. Am I going to stand 10 feet from the painting? Maybe, maybe not. I might stand even closer. So I'm just going to go 0 to 5 initially. I may need to make this number bigger, but I don't think it needs to be big, because we're talking about how far do you want to stand away from a painting. If I stand too far away, my viewing angle starts to get really shallow. And I want to look at this right here. This is a function, right? Input the distance x from the painting, and the output is the angle. So what's a good interval for the outputs? Well, 0 degrees would mean I have no viewing angle at all, and 90 degrees would mean my viewing angle was this, which is clearly outrageously large. So I just eyeball theta and estimate. Is that a 30-degree angle, 40-degree angle? 45 is probably bigger, so maybe I'll go 0 to 45. So come up with some guesstimates that are reasonable for your angles, and then jump to the calculator. So I'm going to hit escape and keep. So we keep that work, and then we're going to pop the calculator open. And so the calculator, I'm going to go in to graph it, and I don't have the option for theta, so we're going to use let y represent theta, and then we'll type in our equation. Our equation was tangent inverse. I'm going to use the second button right here, second tangent, to get the tangent inverse to feed in, and it's going to be 4 divided by x to get 4 over x, and then it was minus second tangent to get the tangent inverse, and the second expression was 1.5 over x, so 1.5 divided by x. And then right now my window, if I click window, it's set to the standard viewing window, -10 to 10, -10 to 10. So the mistake that we frequently make is we go ahead and graph a function without thinking about where the inputs and outputs should live. And if I just hit graph on the standard viewing window, what I'm going to get when the calculator gets around to graphing it is a bunch of junk that is visually not very informative. So really, two things I want to do. I want to make sure what mode I'm in. So I said that theta maybe runs from 0 to 45 degrees. So in terms of mode, am I in degree mode? Yes, I am. Okay, in degree mode, so that's good. And I want to look at my viewing window, and we talked about, hey, maybe letting x run from 0, let it run from 0 maybe to 5, to say, hey, this is going to be a max of 5 feet away. And we can make this number bigger if we need to. X scale, tick marks every 1 is fabulous. Y minimum, -10 degree viewing angle doesn't make any sense. So 0 degree viewing angle means I can't even see the picture. And 45 degrees looked way bigger than what the angle was. But let's see how this graph looks. So we'll graph it. And it's looking pretty good. We could have used under the zoom menu the zoom fit, and then the calculator would have picked the angles based on the input I chose. I chose 0 to 5 feet. It would have picked the vertical axis for me. That's always a nice way to do it. So for example, if I had done zoom, I could have gone down to zoom fit, and you'll see how this changes the picture. Go down to zoom fit and hit enter. And now what the calculator will try to do is optimize this output window based on the input values that I chose. And what you'll see is that it probably more efficiently uses the viewing area in the window based on my 0 to 5 foot input values. So we wanted to maximize viewing angle. So the key is that we're looking for the inputs. The inputs on here, these are our x's in feet, and these are our viewing angles in degrees. So to maximize the viewing angle, I'm looking for the peak on this graph. This peak corresponds to the max or largest viewing angle that's possible. So I need to find the maximum. So I'm going to go and use the calculate menu over here. That's above the trace button. I don't want to use trace like ever, really. So we'll use the calculate. So I'm going to go second trace to get at the calculate menu. And I want to find or estimate the maximum on this. So I'm going to scroll down to maximum and hit enter. And then the calculator is going to ask me to give a number that's to the left and to the right of that maximum. So 2 looks like it's to the left. So I'm going to guess that 2 is to the left and hit enter. And I think 3 looks like it's to the right of the maximum. So I'm going to hit 3 and press enter. And then it wants a guess. Where do you think the maximum is? So between 2 and 3 at 2.5 would probably be a good guess. And I'm going to hit enter. And so what we can see is that it's saying, hey, I'm going to get a maximum viewing angle of 27 degrees when I'm about 2.4 feet away from the painting that's hanging on the wall. So you can see 0 to 45 degrees was too much. And we knew it was, but it was reasonable and gave us a good usable picture. So you wrap the problem up once you do that, and it's a story problem, so I just want to finish with a sentence. So you would say, you will get a maximum viewing angle of about 27 degrees if you stand about, and it says tenths, so 2.4 feet from the picture. And I'm using the word about here on purpose because both of those numbers, if I think about it, they're rounded numbers, so they're not exactly the right numbers, but they're close enough. They're good enough for government work, and life is good.